Hello, welcome back to Piers Rocks. Today we're going to take a look at this 8050 disk drive that's already in pieces. So the reason this disk drive is already in pieces is because I used this as a donor board in a previous 2040 repair. When I fried my bus transceiver, I borrowed a bus transceiver from this board. I've since replaced this bus transceiver with what I think was a new old stock one from eBay, but I've not tested the transceiver. In fact, I've never tested this disk drive. Two reasons why I wanted to work on this disk drive today. One, it's been sitting in pieces ever since I used it as a donor and it's cluttering up the office. The other reason is I wanted to see if my IEEE-488 disk drive diagnostics ROM works on the 8050 and the 8250. From my viewing of the schematics of the 8050 and the 8250, there's really only one significant hardware difference that means that the diagnostics ROM I already built should be incompatible. And that's that the ROMs on the 8050 and 8250 are 8KB ROMs rather than 4KB ROMs. So I've built a new version of my diagnostics ROM which lives at E1000 hex, replaces the top ROM here. And apart from that, I think we should be good to go. There are some hardware differences with the disk drive units in the 8050. They use quad density disks. They're still single-sided, but they can store up to twice as much data on them as the 2040, 3040 and 4040. That shouldn't matter for the diagnostics ROM. The other difference is the 8050 and 8250 has a 6502 secondary processor instead of the 6504 on the older disk drives. On the face of it, that shouldn't matter. There is one slight hardware or circuit difference with this 6502. The 6504 in the older disk drives does not have an NMI, non-maskable interrupt pin. The 6502 does, and this is actually connected in this disk drive, although I'm not sure what purpose it serves, and I don't think we'll have any issues as a result of that. The RAM's the same on this system. It's still 4KB in 4 banks of 1K, and each of the 1K is split between the upper nibble and the lower nibbles. We're still using the MC3446 bus transceivers, still using the 6532s, still using the 6522, still using the 6530, although the ROMs on this system are different, and that includes the 6530 mask programmed ROM, also the GCR ROM up here, and as we've talked about, the main ROMs for the system. Right, I'm ready for the first power on. As it's the first power on, I'm a little bit nervous it might go pop. There's, for example, a filter capacitor on the incoming main supply that may not have been powered on for quite some time. It's possible that will let go, but let's find out. Well, it's powered on okay, and I think the disk drive has booted successfully. You can see that it's had a bit of a hard life. It's missing one of the drive LEDs here. I'm not sure what's happened to that. It might just have got knocked inside. I've not looked. You can see the door clip has come off. Hopefully I can get that back on. It looks intact. But we saw the two LEDs that we have come on solid for a little bit of time, and then the drive LED went out and the main LED is sitting there green. So I think the drive has booted successfully. It's presumably passed all of its power on self-tests. The DOS2 images for this drive I had a look at prior to this, and they do have a lot more self-test functionality than the DOS1 2040, 3040, 4040 ROMs. So for the most part, this looks like it might be working. I'm still going to try it with my diagnostics ROM installed, partly to see if there's any faults that's picked up that the power on self-test from the stock ROM hasn't, but also just to check whether my diagnostic ROM actually runs in an 8050 or 8250. I've never booted this E1000 located ROM in any disk drive, so I might have made a mistake in building and linking it. I've got the diagnostics ROM installed now. In case you're wondering what this extra doobry is sticking off, that's just a programming jig I use for these EEPROMs. The other thing that you may not be able to see very well is I do have the secondary ground point of the circuit board, which is just out of frame, just down here. I have that connected to the chassis ground. So hopefully I'm not going to fry any chips powering on the circuit board out of board. And I think this ROM is properly inserted. It's a little bit hard to get it to seat all the way in the ROM socket. Hopefully that's fine. I now power it on and we'll see what happens with the status LEDs. Actually, there is another hardware difference with these drives that I forgot to mention, and that's that the status LED has the ability to show two different colors, green and red. I think it showed red when it first powered on, then it switched to green. Now, I haven't studied the schematic in detail, but I think that the green is literally just a power LED which has no software control behind it. And the red is the part of the LED that can be controlled by software, just like the older disk drives. So my diagnostic ROM is going to be controlling the redness of that LED and not the greenness of that LED. That's my expectation. Anyway, I'll turn the disk drive on again. So with my diagnostics ROM, I'm getting no boot at all out of this disk drive. So I'm now in the mode of staring at a bunch of code and configuration and trying to figure out what on earth's gone wrong. When an embedded system like this doesn't boot, you're kind of out of luck. You don't have any way of getting diagnostics out of it, so you have to just continually look at what you've done and try and figure out where you've made a mistake and try things until you resolve it. So that's now what I'm in the process of doing, and I thought I'd take you through some of that process. So what we're looking at on the screen right now is the linker file for this version of the ROM to check it's correct. And we can see that I've configured the ROM space to start at E1000 hex. That's correct, that's where I'm trying to locate it, and it'll be 8 kilobytes long, which is 2000 hex. And then I have a number of sections of different items within my ROM. I start off with an 8-byte header. I then have my code, which should be executing. I have some code that will end up getting loaded to the secondary processor. That is deliberately located at FD 100 hex. And then I have some data, strings and such like, and then the reset vectors at the end of the ROM. And the most important vector for us right now is the reset vector, which lives at FFFC. So that's the linker file. This will go through and put my code together into the ROM itself. Now look at one of the 6502 source code assembly files. This is the header source code, so really just covers that 8 bytes. And I do different things based on the variant of ROM that I'm building. I'm going to stick a different byte at the beginning of the ROM to help me identify when I'm looking at the contents of the ROM which ROM it is. And I should be putting E0 at the beginning of a ROM that starts at E1000. And that's just a hash define. But then if we look at what actually should be put into the ROM, this is where the segment starts. So this is where the code actually starts. And I have a bunch of hash if defs or dot if defs in assembly. And in this scenario, where I'm trying to build the 8050 variant for the E1000 ROM, I should be putting that E0 as the first byte. I then should have major, minor, and patch version numbers, a reserved byte, which I think is 0, and then the last 3 bytes are jump to the with stack main routine, which isn't defined in this header file. There's another segment that's defined here, which is the vectors segment, which has the NMI handler, which goes to FFFA, start, which is FFFC. That's the reset vector. That's what 6502 should be reading this address when it boots up and starting to execute code at this point. And then we have an IRQ handler at FFFE. So that's what we're supposed to have. So this is the ROM. I've confirmed this is the ROM that has actually been written to my EEPROM. And it starts off with the E0 byte. That's correct for this image. We have the version number 0.1.6. We have the reserved byte. Then we have the jump to with stack main. And then this is where the actual start routine starts at offset 8 from the beginning of the ROM. So we should find in the reset vector at FFC relative to the start of this ROM, so 1 FFC with the start of this ROM, which will be located at FFFC, we should find a pointer to E008, which is this location here. This is where the code should start executing. I think this is a CLD instruction, clear decimal mode, and this is a SEI, clear interrupts. And then this is load the hex value 18 into the accumulator, and this is then stored at address 0282, which is the address of the port B for the 6532 that controls the LEDs. TLDR, this turns the error LED off and leaves the two drive LEDs on, and we're not seeing that happening. So you can see that happens essentially as the fourth instruction that the processor should be booting. So it suggests we're not even getting to this point of executing the code at 8 offset from the beginning of the EEPROM. So let's go and take a look at the end of this EEPROM at the 1FFC location, which gets loaded to FFFC, and check that that's pointing to E008, which is here. This is the end. That's FFFC, and it's pointing to E008. So that is correct. So at this point, I'm stumped. I don't yet understand why the system isn't booting with my diagnostics ROM in it. I've double checked the memory map for the 8050 and from a document online, and the 6532 that controls the LED has the same register location as on the 2040, 3040, 4040, so that's 0282 location that we saw right at the beginning here. So we should be, if we're getting to here, we should be loading 18 in that register, 18 hex, and that should turn the error LED off, and that is not happening. And then as we go through here, this code here is essentially doing a 0-page RAM test, and elsewhere here we should be turning the LEDs off. Can't immediately see where that happens here. So at this point I've narrowed the problem down to one of 5 things. My EEPROM hasn't written properly. Well, I've verified it in my EEPROM writer, and it has the image that I intended to write to it, which we've just looked at. Second potential problem is I was running the EEPROM with the programming jig attached. I've disconnected it and no change. Third is that the ROM is not making a good contact in the socket. It appears to be making a good contact in the socket. When I replace the system, the default system ROM, the system boots. Maybe it's a problem with the image that I've written. We've just gone through the image that I've written, at least the key parts of it, the reset vector, and then where that's pointing to, so the code it should be executing. And then the fifth potential problem is that the 6532 that's controlling the LEDs is not located where I think it is, or the LEDs are controlled differently. I got this, and I'm pretty sure that it is located where I think it is, in the same location in the memory map as on the 2040 and older disk drives, and that the LEDs are connected to the same pins. So this is the 6502, the main 6502 in the system. This is the ROM that I've replaced, and this is the 6532 that controls via these 3 lines here, PB5, PB4, PB3, on pins 18, 19 and 21, the 3 LEDs. This is the error LED, and these are the 2 drive LEDs. So this one I should be switching off, and I was wrong earlier when I said that the software has no control over the greenness of that LED. What I think this circuit does is it inverts the, I think this line here goes to the green LED, and the above one goes to the red LED, and the green LED is on when the error LED is off. So it basically just inverts the signal with this extra inverter here. So 5 potential issues, and I've ruled them out. But the system is not booting, so either I'm wrong about one of these, or there's another potential problem which I've not thought of yet. Welcome back. I gave up in disgust yesterday after tearing out what remained of my hair. Today we're going to take a look at some schematics. This might seem like a bit of a digression, but it's not. in front of me I have the first 8050 schematic that I'd come across. If we take a look at the document, it's the 4th revision of this schematic, and it's the 8050-001 schematic, which covers the 8050-002 PCB, which is what I have in my 8050. And as far as I can tell, all of the 8050s and maybe all of the 8250s, not the LPs, but the regular 8250s, use the same circuit board with various tweaked components and jumpers. Take a look here. We can see the 6502 here, and then the 2 ROM chips are here, UH1 and UL1. UH1 is the top ROM, the E1000 F1000 ROM, and UL1 is the bottom ROM, the C1000 and D1000 ROM. On this drive, while there is a place on the circuit board for UF1, it's not used. We can see pin 20, the chip select line, is not connected, so that simply can't be used. And that makes sense because these ROMs are 8K in size. So 2 of them together use the top quarter of the address space. And as we'll see, actually the top quarter of the address space is shadowed to the next quarter down of the address space because of how the address selection and chip selection actually works. So I want to take a look at the circuitry for actually selecting the active chip, and that's this part of the circuit here. To select the top ROM, which should be UH1, which is the right hand side as you look at the circuit board, then the top 3 address lines will need to be 1s, and then so that's 13, 14 and 15, and IE12 will be 0 to select the E1000 space and 1 to select the F1000 space. So let's trace through this circuitry and see how it's actually going about selecting the ROM chips. Well, we can see all 3 of the top 3 address lines are going into this binary to decimal converter chip, which is just like the architecture on the 2040, 3040, 4040. Those go in, but the selection of the chips is different to those drives. So where in those drives the top outputs from the binary to decimal converter are used to select the ROM chips, those aren't being used here. IA13 and IA15 are being tapped off and feeding into this collection of NOT and AND gates here. And I'm glad they're not an AND gates because I can cope with the logic of not an AND gates. That's fairly simple. When we get into NANDs and XORs and NUXORs, I struggle a little bit. The reason why IA14 is not tapped into is because, as I said, the top quarter of the address space for this processor is being shadowed into the next quarter down. And that's done because the IA14 simply isn't used in the ROM selection. I also said that I13, I14 and I15 all needed to be 1 in order to select the top ROM. So let's take a look at what happens in this circuit if they're all 1. So we can see I13 is this line here, and I15 is this line here. And we can see they're going into this collection of AND and NOT gates. Now there's one other trace that's coming in to that collection of NOT gates, and that comes all the way from up here, and that's Phi2 coming down from the processor. And I'm pretty confident that the reason for that coming into this AND gate is because the 8050, like the earlier disk drives, is a dual processor drive, and each processor gets to access the data bus, which is shared between both processors 50% of the time, and that's being done using Phi2. So Phi2 is coming down into this AND gate and turning the output of this from this AND gate off when Phi2 is low, because obviously then this input will be 0. It doesn't matter what input 2 is. Output 3 is always going to be 0. Input 1 is 0. And because then we have 2 AND gates that are in series with that first AND gate, if this first AND gate is outputting a 0, then one of the inputs to these other 2 AND gates is going to be a 0. So the output is always going to be 0 from these 2 AND gates when Phi2 is low. So Phi2 is basically just controlling who accesses the bus. So when phi 1 is 1, this CPU can access the bus, and the first input to this AND gate will be a 1. So we'll just bear that in mind. So IE15 comes into this AND gate, and when it is 1 and phi 2 is active, then its input to both of these two AND gates will also be 1. And then we took IE13, and we can see this is going directly into this AND gate and through a NOT gate here before it goes into the other AND gate. So IE15 is selecting that one of the two ROM chips will be active, and then IE13 is selecting which ROM chip will be active. So when IE13 comes in and is high, that should be the top ROM. This AND gate is going to be outputting a 1, and then this chip select line here will be a 1, and this chip select line here will be a 0. And vice versa. If IE13 is low, they'll be active the other way around. Now, some of you may be noticing something a little bit odd at this point, and that's that normally to make a 2364 ROM active, you pull a chip select line low, you don't pull it high. And in fact, you may notice on this schematic here that there's a little circle where the chip select line 1 terminates on the chip. That's done on the schematic to indicate that a pin is active low. So when I was first looking at the schematic, I was thinking these chip select lines are active low, just like normal 2364s. In fact, we can see on this binary to decimal converter, the outputs are active low, which is correct for a binary decimal converter. As I say, the 2364s could be mass programmed in a factory to have their chip select lines operate in either direction. And while this schematic says, through the use of the little circle here, that these are active low, they simply cannot be active low, because when the clock line is low, remember that's turning off the bus for this processor, this half of the disk drive, then the output of these AND gates will be low, and both of these two chip select lines would be low. This one would be low, and this one would be low. And they would not only be both talking on the bus, conflicting with each other, but they'll be conflicting with the bus from the other that the other processor is in the process of trying to use. So these ROM chips have to be active high chip select line ROM chips in the 8050. And this schematic is wrong, because these are indicated as active low. And there's another mistake in this schematic that I passed over, which I said that when IE13 is 1 and IE15 is 1, top ROM will be selected, and that's UH1. Well, if we trace that through, IE13 1, it's 1 going into this AND gate and 0 going into this one. So this one will be 1, so it will be selecting this one up here. This one here will be selected. But that's the left-hand ROM chip, and that's the low ROM. So there are two mistakes in this schematic that I've been referencing. One is these indicate that the chip select line is active low. That's wrong. And this is saying that the top ROM is UL1, and it's not. It's UH1. Actually, I'm quite interested if there were any 8050s that were manufactured with the ROMs swapped around in the different positions. I've confirmed that mine are, I think, pretty sure in the right position. The top ROM is this UH1. But the reason why I think there may have been some that were in the opposite position, even though they were labelled the correct way round, is I found a post on one of the retro Commodore forums suggesting that they found the ROMs, despite the fact that they were indicated with the right numbers, indicating the low ROM on the left, the top ROM on the right, the code on the ROM chips themselves was actually switched around. So I'm wondering if some early circuit boards did actually have this AND gate arrangement down here, selecting left for high and right for low instead of the other way around. They can't have had CS line low, because the circuit the disk drive simply wouldn't work if CS1 was active low, because these would be talking at the same time given this circuitry here. Anyway, this is the first copy of the schematic that I've been doing all of my pre-reading and investigation of the 8050 off. We'll now take a look at another 8050 schematic. So here's the second schematic, and pretty sure this is the same actual diagram as the previous version of the schematic we were looking at. This is still the 8050-001, it's still for the circuit board 8050-002, and I've stared very hard at the two diagrams and the writing on the two diagrams, and I say I'm pretty sure they're the same schematic, but this one has been modified in a couple of key sections. First thing we can see immediately is there's no little circle in front of these two chip select lines. There's still one over here actually in this unused ROM chip. They haven't corrected that, but they've corrected the chip select lines here to be active high on these 2564s. And there's also a difference here. These two lines here, this one and this one, have been switched around to correctly show that when address line 13 is high, UH1 is selected, the right-hand ROM chip, and when it's low, but our IA15 is still high, UL1 is selected. So that's the two errors that I found in the first version of the schematic that I'd been looking at. So a real trap for young players there. And this, it may sound like I happened upon the second version of the schematic and I figured it all out really quickly. I didn't figure it out really quickly. What happened was I just couldn't get my diagnostics ROM to boot in this disk drive. And I thought it through logically and thought, well, I have the ability to write my own EPROMs. So let's write the stock upper ROM EPROM and try that in a disk drive, because I've got plenty of boards that can emulate 2364s. And I did that with three completely different implementations of 2364 replacements. And none of them would work in this disk drive. And after thinking about that for a while, I remembered that I've come across 2332s with the different chip select line behavior. I'd never come across a 2364 with different chip select line behavior, but I started wondering if actually this drive had unusual chip select behavior on those ROMs. And I built myself a little circuit, which I have here, which has essentially a 7404 NOT gate on the chip select line and a stack of sockets to tap into the chip select line coming from the PCB, route it through the NOT gate, and then send it on to the ROM that I install in this socket. And I could get my replacement ROMs to boot in this disk drive. So I've confirmed that the chip select line is the opposite way around on these 2364 chips. Now, at the moment, I'm a little bit stuck there because I only have these crappy round hole sockets for 24-pin chips, and these are not reliable, especially when used with the round pin headers, which is what I've got mostly on my replacement 2364 ROM chips. I don't know if it comes across on the camera here, but I've actually tinned the pins of this ROM chip to try and get a better connection in these crappy round hole sockets. So before I can move any further on this disk drive and testing out my diagnostics ROM with it, I'm going to need to get hold of some of the more traditional wipe style sockets, because I think they're going to be more reliable when used with these round holed EPROM replacements. I also don't actually have very many 2364 replacements at the moment. I have a number on the way. So I'm going to put this on hold until I get some more stock, both of the sockets and the ROM replacements in. However, the drive does seem to boot with the stock ROMs installed. So I do want to do a final test before ending this video to see if it's actually functional over IEEE-488. If you remember from the beginning of the video, I said I'd pilfered an MC3446 IEEE-488 bus transceiver from this disk drive to replace in my 2014 and replaced it with a new old stock one I bought off eBay. I want to check actually, does the IEEE-488 bus work on this disk drive before putting this video to bed. So I have the disk drive connected up to my PC, so I'll reset the bus, and you probably just see the LED of the right hand disk drive up here should illuminate when I reset the bus. There we go, it's illuminated and gone off again. And then we'll query the status of this drive. Hopefully it's device 8. Yeah, there we go, it's talking to us and it's reporting that it's an 8050. We should be able to do a CVM control detect. Yeah, it detects an 8050 DOS 2.5 drive, exactly what I expect. And let's do a command. Let's run initialize drive 0. So this one on the right hand side. I need a drive number. It sounded a bit different from 2040, 3040, 40 disk drive doing initialize. I didn't hear the same sort of head banging noise. I did hear a slight rumbling, which might be head bang on the 8050. Those of you out there more familiar with an 8050 than me will know whether that was the right sort of sound or not. It's reporting an error because there's no disk in the drive. Read error, that's what we'd expect. We'll try initializing the other drive. So it sounds similar. Doesn't sound hugely healthy. Maybe needs a bit of lubrication. Again, we should get a read error from that. So it seems like my 8050 is working. Obviously, at some point, I'm going to need to test out the drive mechanisms. I'll probably want to strip those down, clean them out, lubricate them before I use them. But actually, more important, more urgent for me is to see if my 8050 diagnostics ROM actually works on the 8050. So hopefully we'll see that quite soon when I get some other replacement 2364 ROMs and some different sockets to build a jig that can switch around that chip select line. Well, I don't know how that was for you, but it was a bit frustrating for me, as may have come across in the video. But I've learned more about the 8050 disk drives. I know that, at least in this drive, the 2364 ROM chips have an inverted chip select line. I'm not going to make that mistake again. I'm going to be more paranoid about 2364 chips in other equipment that I come across. We'll definitely be seeing this disk drive in future episodes. As I said, I want to see if my diagnostics ROM can work in the 8050 and the 8250 disk drives. So if you're interested in that, do stick around. If you enjoyed this episode, if you got something from it, please consider sharing it with a friend. Till next time, rock on.